Greetings and salutations. Welcome back to the podcast. Today, we're delighted to be joined by Professor Mark Moldwin from the Department of Climate and Space Sciences and Engineering at Michigan. He did his undergrad at the University of Alaska in Fairbanks and did his PhD at BU in astronomy and space physics. His research over his career has largely centered around space weather and plasma physics, and we're very excited to discuss some of these concepts with him today. Outside of teaching, Professor Moldwin is also an executive director of NASA's Michigan Space Grant Consortium and has been the principal and co-investigator of over 75 scientific projects, including building magnetometers that are launched into space. Professor Moldwin, thank you for being with us today. We're very excited. How are you?
Great. Happy New Year.
Thank you.
Sounds like a lot of fun.
Thank you. Happy New Year to you too as well. And so as Joe mentioned, you went to school in Alaska and you studied physics there as an undergraduate, just like Joe and myself. And now, not only now, but also throughout your entire career, it seems like you've had a focus on the Earth space environment, and specifically the magnetosphere and how that operates, whether it be designing or building instrumentation to study that part of our Earth space environment. And so I was wondering, well, I think when people think of Alaska, the first thing that comes to mind is its beauty and, of course, the aurora borealis. And so I was wondering, that's the most, I think, when people think of space weather, that maybe the first thing that comes to mind is perhaps the aurora and how the sun and the charged particles interact with the atmosphere. And so I was wondering, what kind of influence did that have on your career? Because is it just a coincidence that you went to school up there, ended up studying physics, and now here you are heavily involved with the magnetosphere and instrumentation related to it? Or what did that have some kind of influence?
Yep, definitely the Northern Lights were one of the big attractions. My roommate in college, he was actually from outside, which is the term Alaskans use for everybody outside of Alaska. And he was, so when the first big auroral display happened that we noticed, we both ran outside and it was below zero.
Mm-hmm.
So we're hopping around trying to stay warm, and that definitely captured my attention. And University of Alaska Fairbanks has a large geophysical institute, and part of that is to study the space environment of the Earth and the aurora. And there's a rocket range, a NASA rocket range, as part of UAF to fire payloads into the aurora to study it. And then there's also a lot of ground-based instrumentation, cameras and radars and all types of things. So I actually started working as an undergraduate research assistant my first year with space scientists. And so that got me into the field, and I continued working with Shinaka Sofu, who became the director of the Geophysical Institute, and he's famous for developing the first model of an auroral substorm, or essentially, when you think of the aurora, it's often, it's there 24/7, but during the summertime, you can't see it because the sun is up. And during the wintertime, it can be a fairly narrow band of light, so you have to be at the right latitude, and there can't be clouds so you don't see it every night. But Fairbanks is unique that it's under what's called the statistical oval, so where the aurora occurs most often. So Fairbanks is a great place to study the aurora. But he found back in the 60s that the aurora has certain repeatable behavior, and he named it a substorm, where you can have an arc, or essentially a bright ribbon of light, often green, and the color of the aurora depends on what atom or molecule is being banged by the charged particles coming down the magnetic field lines. And he found that these things happen 4 to 6 times a day, have a time scale of tens of minutes to an hour, but suddenly you can have the entire sky just explode with light. And so you have this huge onset, and dancing filaments of light. And so that's what my roommate and I saw the first time, was my first substorm, to see this, one of the natural phenomena, wonders of the world that everybody should see at some time.
And so I read your textbook.
Oh, wow.
Which I got from the library. And I was fascinated because I've been studying physics for quite a while now. And I guess thinking about the aurora is something I should have done before, but I never really had. When did people start to become conscious of exactly how the aurora was produced and, start to try to understand the science behind it?
Yeah, so I mean, the aurora have been observed in the heavens for a long time, but scientific investigations were sort of slow during sort of the Renaissance, when people were first doing some triangulation, trying to figure out how high it is, and there are a lot of ideas on what it actually was, but it took until really the last century for people to dive in, and when we started to actually understand what the space environment is made out of. It's sort of hard to think about, but most of the great physicists, the Kelvins of the world from the 19th century, they didn't even know about electrons or ions, and so a lot of the plasma state was not there. And even though Maxwell was able to describe a lot of the work done by 19th century physicists like Ampere and Michael Faraday, and tie it together, actually think about that space is not a vacuum, took a while. And one of the leaders is a Norwegian scientist, Birkeland. And last year, 2 years ago, I went on sabbatical at the University of Bergen in Norway at their Birkeland Center for Space Science. And he was really the first physicist that tried to explain the connection between the light and some of the activity, the electromagnetic activity that you can observe on the ground. And so that's what I do right now, is I build magnetometers that measure magnetic fields. And if you remember from your intro physics, Ampere's law or Biot-Savart, if you have a current, you're going to create a magnetic field. And so the aurora are actually currents flowing from outer space into the upper atmosphere of the Earth. And because it's an ionized layer, the ionosphere, the currents can flow, there's conductivity, and then go back out into space to close that current loop. So there's essentially a motor running in space that is creating this EMF, this voltage or this current. And as those electrons flow through the ionosphere, they bang into particles and cause them to glow. So that's what we see as the aurora.
And then in terms of like also adding on to the history of the aurora and also like the magnetosphere on Earth, was it more that trying to figure out what the aurora was led to figuring out that there's this giant magnetic shell that surrounds Earth? Because at least historically speaking, I think that like in the late 50s and 60s, when we started launching more satellites, or started launching in the first place satellites into space, I imagine that there are a lot of issues with launching things and realizing that there's like this giant magnetosphere around Earth that like damages the satellites. And so did they know before launching things into space that this could be an issue, or did kind of launching things into space like further accelerate kind of our understanding of the aurora and the magnetosphere?
Geomagnetism is a lot older, with some of the Webers of the world making magnetometers and realizing that the Earth has a magnetic field. And it's about 400 years ago now, is Gilbert wrote a book, The Earth is a Magnet, essentially, that he showed that the Earth's magnetic field at the surface looked like a dipole kitchen magnet. And so the development of sensitive compasses followed. And so part of the rise of the British Empire was because of the development of navigation, including using the geomagnetic field. And that led to the development of very stable clocks, so you could figure out your longitude and all types of things without being able to see the star. And so the British and the Germans, von Humboldt, back in the early 1800s, proposed setting up geomagnetic observatories around the world. And so one of the things that people noticed was occasionally that the compass needle of the magnetometer wiggled. And it was noticed early on that those wiggles often were associated with aurora. And so you had to, I wonder if it's just a coincidence or is there some causal relationship? And so people had been thinking about, is there some type of electrical currents flowing? And that's what led Birkeland to think, well, if I can explain this with, if there is a current flowing in the atmosphere, and then they had to figure out, what it was. And with the discovery by J.J. Thomson that there are electrons, then we could start thinking that the space might be filled with these charged particles that can enter. And so there's a lot of suspicion and a lot of early work. A lot of Nobel Prizes were given to folks discovering the ionosphere and recognizing this electrical ionized layer. And even comets. I just saw that there's a comet that was recently discovered. It's now between Mars and Jupiter, but it already has a tail. So they're hoping that it might be a visible comet in 2021. But comets have been observed since naked eye astronomers. And one of the things that was interesting is people noticed that the comet tails always pointed away from the sun, and it didn't matter if they were coming into the inner heliosphere or towards the sun, or if they were going back out. The tail always pointed away. So it was hypothesized that there must be something flowing from the sun, and this radiation pressure and such wouldn't explain all of the tail. So people postulated that there must be some type of matter coming from the sun. But if you calculate the equilibrium temperature of the sun, which Kelvin was able to do, it's 6,000 degrees. And then if you then realize that it's a gas ball, you could calculate what the escape velocity of an electron would be, and it's not hot enough. And so most people thought it was a very static, hydrostatic equilibrium ball that was not going out. But we now know that the magnetic fields of the atmosphere of the sun can convert their energy into particle energy. And actually the upper atmosphere of the sun is much hotter than the surface of the sun. It can be millions of degrees Kelvin. And so that's much hotter than the gravitational force holding it down. And so we now know that there's this supersonic flow coming out of the sun, the solar wind. And so that not only pushes comet tails, it runs into the Earth's magnetic field and creates the magnetosphere. And so people started to put that together in the 50s. And then with the launch of Mariner, the first interplanetary probe that had magnetometers and plasma instruments, they actually discovered, yes, there is a magnetized plasma in interplanetary space. And so we've been studying that and trying to connect the dynamics and energy flow from the sun and how it impacts the space environment ever since.
And so I assume that many people who hear about space weather, I think a lot of people have heard that radiation is damaging to astronauts, and then maybe have heard of stories like those great magnetic storms that disrupted power lines or things like that. But what is sort of the objective of the practical objective of trying to understand the space weather? Is there a practical objective, or is it one of these things that's still just being pursued for the sake of trying to understand something better, and that one day we hope will result in something real?
So space weather it is actually one of the big applied physics topics now in space science, because it's really interested in how the energy and matter from space not only impacts the space environment, but specifically how it impacts technology and society. So as we're now a spacefaring civilization, we've had humans off the surface of the Earth all your life, now with the ISS hitting 20 years old. And the activities of NASA's Artemis mission to get back to the moon and going on to Mars, either through government, the Chinese or the US, or even commercial Elon Musk type activities. We're going to be living in space, not only protected by the Earth's atmosphere and magnetosphere, but suddenly now out exposed to the environment of the sun. And so over the last few decades, we've recognized that what goes on above our head a few hundred kilometers can have a big impact on our cellular communication, our GPS navigation, our power grids, even our fiber optic cables that go transoceanic. All of those have big space weather impacts.
And are we capable yet of having sort of a space weather forecast in the same way that we have a weather forecast on Earth? Because, for example, if I were going to go, say, climb a mountain or cross an ocean, I would check the weather forecast beforehand. Is there an equivalent with space weather that that's starting to exist where, for example, before launching satellites or people, we can check and try to understand the coming environment better? Or is that not yet possible?
Nope, but NOAA, the National Oceanographic and Atmospheric Administration, is charged with making those forecasts. And just like there's a National Weather Service, there's the National Space Weather Prediction Center in Boulder, Colorado, that's charged with making forecasts of space weather. And they have lots of customers, airlines. As we have more and more transoceanic flights, if you make a great circle from mid-latitudes, like from China to the US, going over the pole is actually the shortest distance. And there are two impacts of going over the pole. One is you lose sight of ground stations. There's essentially nobody there, so you can't use your HF radio consistently. And also you're now at the polar regions. And the reason why the Aurora Borealis and Aurora Australis, or the northern and southern lights, are at high latitudes is because the charged particles can flow along the magnetic field. There's no Lorentz force acting on it, where if you remember from your physics class, there's a right-hand rule, QV cross B. So if the velocity of the charged particle is perpendicular to the magnetic field, there's a force that's going to try to deflect it. But if it's along it, it can move. And since the Earth is like a dipole, the field lines are coming in and out of the polar regions. So the charged particles get funneled into the atmosphere at the high latitude regions. And so the radiation environment over the poles is much higher than at mid latitudes. And so airline crews are considered by OSHA, our Occupational Safety and Health Administration, and the equivalent agency in Europe, as radiation workers. And so there are radiation monitors on all commercial aircraft, so they can monitor the dose. And everybody has dose limits for your career, as well as an annual dose limit. And so in one storm, you can get a yearly dose. And so instead of grounding that crew, and instead of pilots, what they would do if NOAA forecasts that there's going to be a geomagnetic storm, they'll go at a route that doesn't go across the poles. And that's a longer route, so it's more fuel. And so they don't want to do it, but they don't want to pay people to be not flying. So they do make forecasts. Power companies respond to forecasts to try to make the grid more resilient. And then communication and navigation, exploration depend on knowing what the Earth's magnetic field is. And when these storms happen, the Earth's magnetic field starts wiggling. And so if you're trying to use the Earth's field as a good compass during a storm, it doesn't work. or if you're trying to look at oil exploration, and you're trying to discover different conductivity layers in the Earth, you don't want to do it during a geomagnetic storm.
Okay. And then how concerned should people be? Because the sun is obviously 1 AU, or like 93 million miles away. So it seems very far, except its implications and its things that can do to our technology here on Earth is only 8 minutes away in terms of light travel speed or time. And so is this something that we can kind of somehow prevent in our technology as we launch things into space? Because it seems now more than ever, obviously, we're a very communicated and like intertwined society where there's no longer like geographic or like political borders in terms of like we're all connected with technology. And so like should people be concerned about like the sun and like are we okay just like here on Earth, or should we be all downloading the NOAA forecast, seeing if tomorrow there's gonna be some massive solar storm?
Well, personally, in terms of health, we evolved on Earth with our star, and so we have the protective envelope of the atmosphere and the ozone layer and the magnetosphere to protect us from both the electromagnetic and the charged particle radiation for the most part. But as you mentioned, our technology now depends on a lot of things that happen in space, and we also have global networks, so essentially long wires going all over the place. And one of the Faraday's law of if you have a DBDT, you have a time-changing magnetic field, you'll induce an EMF in a long wire. So that's how a generator works. And so again, a geomagnetic storm is changing the Earth's magnetic field. So you have a DBDT, and these auroral currents can be very dynamic. And so you have a changing current, you have a changing magnetic field. And so that is the concern for blackouts. And in terms of risk assessment, there's sort of two global risks that we can do something about. One is a pandemic. We haven't been doing very well. The other one is a large geomagnetic storm that knocks out regional or global communication and power systems. And because our society is a very complex coupled system, and it's sort of just to think about the light, our internet, the food we eat, the water we drink, our transportation systems, all of them are dependent on other systems. Our waters needs electricity because they have pumps. And so a failure in one can have a cascading failure. Financial systems, if suddenly the internet went down. And so there's a lot of effort to try to understand what those risks are, how to mitigate them, make the systems more resilient, more redundant, or protect them. Like a good engineer, if I know I have a cell phone that most people drop at a meter, can I make it so it will survive a meter fall? And so I can make thicker aluminum housing or whatever it is to try to protect it, airbags and seat belts and crumple zones and radar and all types of things we can put in to try to prevent the accident. But as Joseph was mentioning, the other thing is prediction, right? So for a hurricane, we haven't had mass fatalities due to the impact of a hurricane like we did prior to the space age, where communities were hit with a storm because they didn't know it was coming. Now we have the ability to see the storm coming, make forecasts on its track and its intensity, and do evacuations. The same in space weather is we're trying to make predictions. And if we know a storm is happening, we can put satellites into safe mode. We can have astronauts go deep into the ISS so they have the most mass around them. When we schedule astronauts to the moon, we can attempt to make forecasts on activity on the sun, et cetera.
And so Earth has this magnetic shell that protects us from a lot of the solar radiation. And that's due in part to all of the liquid metals under Earth's surface that churn and create this giant magnetic field. And what's the case with, say, the future of human exploration to the moon and to Mars, as you're mentioning? Should astronauts be more worried on environments like that? Are there magnetic shells that will protect astronauts on Mars and the moon? Or how does NASA go about kind of trying to understand the implications, not only on the ISS, but for these future long-term duration missions?
Yeah, pretty much all the planets, except for Venus and Mars, have this intrinsic magnetic field that's created by the dynamo of the liquid iron cores, so deep inside the Earth. And the magnetosphere does protect us because of this Lorentz force. As charged particles are streaming towards us, it sees the northward magnetic field and gets deflected around us. And so when you leave the protective cocoon of the magnetosphere, suddenly you have direct access to these very high energy solar particles, solar energetic particles, but also cosmic rays coming from outside our solar system. And those bathe the interplanetary space and the planetary environments. And right now, that is the limitation for human space exploration, is radiation. That you can easily forecast lethal doses due to large solar storms. And we've been lucky so far. We've had 12 astronauts with the Apollo program land on the moon. And Apollo 17, which was the last Apollo mission, sort of got lucky that if it had launched at a different month, we had a 50-50 chance that one of the astronauts would have gotten a lethal dose while they were on the moon. There was a very large geomagnetic solar storm in 1972. So that is a concern, and part of it is the total dose that you get. So when you think about radiation, it's it's a little bit confusing because there's different types of radiation. There's electromagnetic radiation, X-rays and gamma rays and ultraviolet, and then there's charged particle radiation. There's electrons, beta, and alpha particles. And then you can imagine like cosmic rays, they're essentially the nucleus of the entire periodic table, so iron. And so they can have huge amounts of energy. And so depending on the energy and the type, they interact with the human body differently. So the eyes and the skin and our blood forming organs have different sensitivities, different energy ranges. And you can have an acute dose, so essentially get a blast, sort of like Doc Bruce Banner belted by gamma rays and turning into the Hulk. You get a big blast and have damage to your DNA and your cellular structure. But you also can have chronic exposure. So if you're living near a uranium mine, you're going to have a higher background radiation dose. And those can have different health effects. So astronauts would have to be worried about both. So I'm going to be in a higher radiation environment if I'm living on the surface of Mars, and I'm also susceptible to large geomagnetic or solar storms sending solar energetic particles your way. So they have to be very thoughtful on how to provide shielding as well as forecasts. So,
and how can we shield better? Because from what I've heard, it's just I've heard nearly exclusively, oh, just dump just have a huge vat of water between you and the radiation source and you'll be safe. But obviously that's not super practical if you're in space and everything is weight cut to the absolute limit. So do we have any idea on, is there a promising lead on how we might deal with this, or is this still a huge unsolved for astronauts?
Yeah, so it's a tough nut to crack. So if you've been to the dentist and had a tooth x-ray, one of the things that the dental technician does is put a lead apron on you, and then they walk out of the room, right? Because even though they're x-rays, they're ionizing radiation, and they have a lot of medical benefit. They don't have to cut into things to see inside, but some of that energy can be deposited where you don't want it, and can cause some cellular or DNA damage. Fortunately, you know, we've evolved on a planet that has radon and uranium and cosmic rays, and so we have DNA in all of our cells and ability to correct errors. But that also gives rise to sort of evolution, because we have changes in our gene, our DNA, and that provides evolutionary change. So if you're following COVID, you know it's had 23 different mutations already as their sort of survival of the fittest. Some of the mutations are more successful, and we have new variants now that are more contagious. And part of that is through just errors in genetics, but some of it is due to damage. And for the shielding, that would be great. Just put lead, aluminum, water, whatever you want between you, or if you're on the moon or Mars, live underground. And so part of the current research right now is we've discovered that looks like lava tubes, or essentially caves, on both the moon and Mars. And there's a new NASA challenge for students to develop a spelunking robot, because it's sort of like, hey, Joseph, why don't you go explore that cave? And then it'll be sort of a Star Wars type of thing as you have Minox flying around, but who knows what's going to go on. But that would be a very easy, you don't even have to dig, just become a spelunker, and you have a place to live. And then you have all the regolith, all the dirt between you and the radiation. And so a shovel will probably be one of the key things to bring with you if you're one of the early explorers, to try to get as much mass between you and space.
And so we saw that a lot of your research is about making or putting magnetometers in interesting places and understanding the data that comes out of them. So what is it that you do? For example, do you design the actual magnetometers themselves, or do you find interesting places to put them and new ways to extract data? What does a space scientist do on a daily basis, or someone like you?
So there's a lot of different ways to measure things, including magnetic fields. And the classic space-based magnetometer, it's called a flux gate magnetometer. So pretty much every magnetometer that has flown on Galileo, on Cassini, on almost all of the Earth orbiting spacecraft are flux gate magnetometers. And so they've been around in space longer than I've been on Earth, so the last 60 years. And as we've developed our capabilities in electronics, they've continued to shrink and shrink and shrink and have low power. But one of sort of the key scientific or engineering innovations is if you can reduce a parameter by an order of magnitude, or increase it by an order of magnitude. So if I'm a telescope builder and I can collect 10 times more light, or I can have 10 times better resolution, that is a huge advance, and you're going to win a lot of prizes or become really rich. Or if you're an automotive designer and I can increase fuel efficiency by 10 times, so 400 miles per gallon or whatever, right? So order of magnitude is sort of these big jumps. And for electronics, they often call what you're trying to do is reduce swap C, size, weight, and power plus cost. And so if you think of your computer, we've had this thing described as Bell's law. So essentially you had building size computers, and then room size computers, then desk size computers, and lap size, and then pocket size with our phones. And now we're going to little microcontrollers that are the size of a pinhead. And once they get that small, you can think about Internet of Things. I can have smart cities where everything is a computer or a sensor communicating with each other. And so now we have this huge network. And so what I've been doing over the last 8 years is trying to take advantage of this mobile phone revolution. For the last 2 years, over 1 billion smartphones have been sold. And so there's a magnetometer, there's accelerometers, there's gyroscopes, there's GPS receivers, there's Wi-Fi antennas, there's Bluetooth antennas and transmitters, there's cellular cameras, microphones, right? There's a ton of sensors, thermometers, and somebody made 1 billion of them. And so it's because the costs and size and power have really shrunk. And so the magnetometer that's in your phone is really crappy in terms of scientific resolution, the smallest field or the smallest change of magnetic field, but it's revolutionary. We actually have a model, sorry, in your phone, the world magnetic model. And so your compass, your magnetometer now helps your Google Maps have a little blue headlight. So your blue dot shows you where you are from GPS, and the headlight shows the direction you're facing, because there's a GPS that tells you your latitude and longitude. And so then you know your declination of the magnetic field between true north and north, and they can figure out exactly where you're, so you can do Pokemon Go and know what you're looking at. But these guys are less than $1. And so a fluxgate magnetometer for a spacecraft is over $1 million. And so if I can say, I can build a space-based magnetometer for 100,000, that's an order of magnitude, then I can start thinking, well, I should have a magnetometer in every spacecraft. And that's what I've been trying to do. And so the last 8 years, I've been working with a company in California called P&I that makes a chip-based magnetometer. And it uses a new type of technology. It's called magnetoinductive. And it's essentially a little circuit, LR circuit, a inductor resistor circuit. And if you remember from your physics class and your Kirchhoff's laws, that all these LRC circuits have time constants and depends on the values of the different components. And you can, essentially every piece of electronics is some combination of inductors, capacitors, and resistors in series or parallel. And we have computers and all types of things that we can measure. And so we've been trying to improve the sensitivity of these magnetometers to become research quality. And in the last few years, we've made really big strides. And so recently, last year, we were selected by NASA to participate in the NASA Artemis Lunar Gateway platform. So the Artemis program is NASA's effort to have the first woman and next man on the moon. So the original goal was 2028, then it got moved to 2024, and it probably get moved back to 2028 because it's hard. It takes a lot of effort and money to do it. But they're launching Gateway, which is going to be a lunar orbiting space station. So it'd be like a mini ISS, but in lunar orbit. And it's going to have a huge ion electric propulsion system. So it can sort of essentially raise and lower its orbit around the moon, depending on if it's going to be picking up Orion crew capsules from Earth, or is going to be dropping down rovers or whatnot onto the surface of the Earth. And we're going to use it as a solar wind monitor. So we're going to be putting energetic particle and plasma and magnetometers on it so we can help predict space weather for the astronaut in the moon.
And this just occurred to me right now, but when you're trying to predict space weather, I suppose there's two ways you could go about it. You could either try to look at what's going on around the Earth and see if that matches patterns that we know, and then predict how it's going to go in the future. Or I suppose you could also look at the sun and try to see what the sun is going to do next and how that's going to influence the space weather around Earth. Which is that something? Do people actually look at the sun and try to predict space weather, or is it more restricted to what's going on around Earth and trying to set up satellites that can understand the magnetic fields and the likes?
Yep. So solar and space physics tries to be able to understand what's going on the surface and even inside the convective layer of the sun to predict sunspots, which are regions on the sun that have very strong magnetic fields. And there's a process called magnetic reconnection that can take magnetic energy and cause a huge release, many atomic bombs worth of energy in seconds. And so those are the solar flares and coronal mass ejections. And so there's a lot of effort looking at the sun to try to understand what the configuration of the solar magnetic fields and plasma are, and trying to see if there are certain types of structures that are conducive for a storm to take off. So it's similar to the National Weather Service looking out over the Atlantic, and they'll have, tropical disturbances that here's a low pressure region that has cyclonic motion. And so we're going to be watching that thing. And then suddenly if it has certain level of winds, we're going to call it a tropical storm. And so we can do the same things on the sun. We number the sunspots and we can start watching them as they evolve. We also, the ability to know what's coming out of the sun and what's going to hit the earth is not very good. So we also have spacecraft between the sun and the earth. And so even though we're 8 light minutes away from the sun, and even though the coronal mass ejection can be going 1,000 kilometers a second, it still can take a day or 2 or 3 to go at 1,000,000 miles an hour. Across 93 million miles is 93 hours, right? So if we are able to see that at Mercury or at Venus or even closer up, that would give us some type of lead time. Yeah, unfortunately, if I put a satellite at Venus or at Mercury, Kepler has those orbits faster than the Earth, so it won't be between the sun and the Earth very often, so it's not as useful. So the Lagrange points, French mathematician figured out that there are 5 points around bodies that are gravitationally stable. And the new James Webb telescope is going to be going to a Lagrange point on the backside of the Earth, beyond lunar orbit. But we have satellites that are orbiting L1, which is between the sun and the Earth. So even though it's about 220 Earth radii, so you can put 110 Earths between us and those satellites, it will orbit at one year orbit. So it always stays between us and the sun. And that distance is about 45 minutes of lead time. So the satellites get hit by whatever's coming from the sun, then we can fire it off with a radio wave at the speed of light. And so we can get a 45-minute head start that, hey, something's coming, batten down. And so we can make forecasts. And there are ideas to put one at other Lagrange points, since the sun is rotating and the stuff comes off the sun is going to hit points on the west side of the limb first before it rotates to Earth. If we have one at that Lagrange point, we could even get longer lead time. So there's a lot of effort to put these sentinels, these space weather monitors. And we have 2 spacecraft, solar orbiter and solar probe, that are going really close to the sun. And at the University of Michigan helped build instruments. Justin Casper and Sue Lepre are the faculty who are the PIs on these instruments. And they'll be able to try to help our understanding of what's on the sun, what comes off of it, and how it evolves between us and the sun.
So essentially, by attaching these magnetometers to all these satellites that we launched into space, we're in a sense expanding our space weather forecast stations.
Yep. So the plasma, energetic particles, and magnetic fields, that tells us what we need to know.
And then was that also a magnetometer that would have been attached to the Voyager 1, Voyager 2 spacecraft? Because I remember a few years ago, it was a big deal in the news when it passed through the heliopause and quote unquote entered interstellar space. So would that have been a magnetometer attached to those spacecraft that would have detected that?
Yep. So they had a magnetometer, and one of the problems with the magnetometer, whenever you have a boundary, there's usually a magnetic shear or a rotation of the field. So the magnetometer is usually it's pointing that way, and then suddenly it points another way. I went through a current layer or a boundary. But if the magnetic field on one side of the boundary and the other either has a very low shear or even no shear, then I wouldn't see it necessarily. And so there are other instruments on board the Voyagers, including cosmic ray instruments that were measuring the intensity of the radiation. And those also saw very dramatic changes when they started to go through these boundaries. So they had multiple instruments to be able to identify what was going on.
And is sort of the ultimate objective of understanding the space environment around us and elsewhere in the solar system, is the ultimate objective to try to get a better and better forecast on space weather, or are we in the process discovering that there are other things that or are we, for example, or are there sort of ulterior motives? Are we trying to understand something deeper and studying space weather is sort of a vehicle to get there? Or is sort of the end goal to just have a complete theory of how space weather works?
So one of the attractions for me for space physics is you mentioned I have my PhD is in astronomy, and the handy dandy rule of thumb, the difference between astrophysics and space physics: astrophysics is everything outside the solar system, space physics is everything inside. And one thing I like about space physics is we get to build robot satellites to go, and we can ask a question. I wonder what the Galilean moons are made out of. And then we go and we say, oh my goodness, it's made out of water ice. And then I have a magnetometer that discovers there's a liquid water ocean. And then you say, well, wherever we have liquid water on Earth, there's life. I wonder if there's life on Europa. And so then we can say, well, let's go. And so we're going to be building a lander. So my lab, we have a grant from NASA to develop a magnetometer that would be able to survive on the surface of Europa for a future Europa lander. And just like on Earth, we can use magnetometers for remote sensing of what's going on in the Earth. Salty water has electrical currents, so I figured out there's a ocean with a magnetometer on Europa. We can figure out if there's plumes, if there's any subsurface hydrology, vents. We can try to figure out thickness of ice layers. So there's all types of things we can do. So we've been trying to do that. So space weather, space physics both has the societal implications as we are becoming dependent on global communication and navigation systems and continental scale power systems. We're more and more dependent on space weather, but there's also a lot of sort of these deep fundamental questions. Mars, we know it had oceans in the past. Where did it go? And what role did the magnetosphere have in protecting the atmosphere of Mars? Because every time a water molecule gets disassociated into hydrogen and oxygen, the hydrogen flies away, I've lost water. And so NASA has a mission called MAVEN, which is orbiting Mars right now, and it has instruments, including a magnetometer, to try to figure out where did the water go? What's the current loss rate of water from Mars? And so there's a lot of deep questions. And one of the universal aspects of planets is it seems that they have, at least for interesting planets that we think potentially are habitable, have an atmosphere, trying to understand the role of the composition of the atmosphere and the interplay between the exoplanet's magnetic field with the stellar wind of whatever star they're orbiting. And so if is there aurora on all these other planets, can we observe it? And if we can, then we have a spectral signature of what the atmosphere is made out of. So suddenly I can remotely sense, or if it's a really strong magnetic field, it's going to become a synchrotron radiator if there's a radiation belt. And so I can measure remotely what the intensity of the magnetic field is of a exoplanet or another planet. So there's a lot of reasons to study the magnetic field.
And so is there a connection between sort of the space climate around Earth and the actual climate, the clouds and the winds and stuff like that? Well, the sort of, I guess, the normal weather, because I suppose there is solar wind outside, but air wind. Is there a connection between the space weather and the Earth weather, or are they generally disconnected systems that don't really have much interplay?
So in general, they've been disconnected, but we know that they are connected, and that there's a lot of decadal signatures in our tropospheric climate, our human weather, and the sun's activity has a decadal oscillation we call the solar cycle. And so we know that there's temporal correlations between a lot of El Nino, La Nina, North Atlantic oscillations, all types of things have quasi 10-year periods. And is it pure coincidence or not? Or if you look at tree rings or ice cores, you can find decadal oscillations. And so the question is, what is that connection? And part of it is from the sun. The amount of cosmic radiation that comes into the inner heliosphere or the inner solar system that hits Earth depends on the solar cycle. So more or less radiation. And as those cosmic rays come through our atmosphere, they change the composition by disassociating. They excite atoms as they bang into it, and the excitation determines the chemical reactivity. It can create nitrogen oxides, NOx's, which have a big role in ozone chemistry. And so you can start thinking of how stuff from outer space impacts the upper atmosphere of the Earth and can find its way through vertical winds and motion to transport one chemical species into the stratosphere, let's say, and then you can change the ozone dynamics, which then change the UV flux on the surface, which then, right? And so there's a lot of things we know are happening, but we're not yet sure what the actual role is. There's a stratospheric sudden warming event happening right now, and we know that has a big impact in the ionosphere and upper atmosphere dynamics, but it also plays a role in weather dynamics. And so there's that coupling, but it's a very sort of emerging field of Earth and space science that really does connect the surface to the sun. And so one of our goals is to have whole Earth, whole atmosphere models from the sun to the mud to try to figure out how all the mass and energy and momentum goes all the way from the sun to the surface.
And to get there, are there still sort of big open sort of, I guess, theoretical questions, or is it a question now of being able to model that physics more efficiently? So that might not be very clear, but for example,
sure.
We have, you talked about Lenz's law and all the various, these various electrodynamic phenomena, which I think we understand sort of on a case by case individual basis. Is one of the objectives trying to understand sort of this electrodynamic interaction at a more fundamental level, or is a big part of your research trying to be able to model large systems of these interactions more efficiently?
So in general, there are still a lot of $64,000 open questions where we have hints, and we're starting to develop experiments and missions to try to solve it. One, the Parker Solar Probe is designed to try to figure out, why is the atmosphere of the sun so hot? What's the mechanism? Waves, magnetic reconnection, turbulence, what's going on? And so we think we know what the potential candidates of the physics are, but we don't know which actual one is. But one of the strange aspects of a lot of science is that when you serendipity, you find things you're not looking for. And so that's sort of a lesson for any scientist, is that don't be blinded to things that you're not looking for. Sometimes we are so focused that we're looking for this one thing that we don't notice something else that is right. So there are quite a few parts of the space environment that we're still struggling with. My research primarily is interested in understanding some of these small scale features of the atmosphere. And the problem with any space science, if you have a single observation, you have what's often called a time-space ambiguity. If I see a change in a parameter, so I see the magnetic field change from a single spacecraft, I don't know, did I go through a boundary?
Yeah.
Or did everything just change? And so what we're trying to do, the ways you can solve it is, one is through statistics. I'll have a satellite in orbit of the Earth, and every time I'm at the same distance away from the Earth, I see the same signature. So it's probably a boundary, and I can start defining that boundary. Or I can fly two spacecraft, and do I see the change simultaneously at both? Or do I see it one and then the other? And then I could, and so the problem with a lot of the space environment is the structure, the scales go from electron scales, meters to megameters, right? I mean, so how do you measure all those different scales? And so that's one of the goals that I've been trying to do, is instead of having single or two spacecraft, why not 6 or 12 or 100 or 1,000? And you can't do it if everything is a couple $1,000,000 each. But if it's $100,000 each, or $10,000 or $1,000, you know, how cheap can you make it? Then you can start thinking of having more and more sensors. And one of the interesting aspects of science is that the higher time resolution we observe something, or the different scale, we see things at finer and finer scale, we discover new physics. And so we're still going, discovering new things.
And then where does the funding reside for like research like this? Because it seems that in the past 2 decades or so, there's been a large shift with NASA and other space agencies in terms of focusing our attention on climate change, as well as like a push towards the moon and Mars. And so it seems that like space science is, as I mentioned like in the beginning of the podcast, I think a lot of people initially just think of the aurora, and maybe they think of something they saw in the news or some History Channel show before about the possibility of a solar storm and it wreaking havoc on Earth and technology. What's been like the progress in terms of funding? Like, is there enough public attention on things like this and your research and similar space weather pursuits?
Yep. So with the creation of Homeland Security, one of the things that the federal government did was to try to identify risks. And so there, you know, from chemical plants to homegrown terrorism. And so there's a long list of risks. And as I mentioned, pandemics and space weather are two of the really big ones. And so our senator in Michigan, Gary Peters, has led an effort to get legislation passed to have coordination and increased funding for space weather, both the research as well as the operations, trying to predict it. And when you think of in the federal government, who uses space, it's essentially everybody. And so part of the issue is trying to get that coordination between NASA and NOAA and all of the DoD intelligence community folks to try to understand what's going on, be able to predict it, try to, what type of design should we have for a space vehicle that will increase its life. And then with the advent of the commercial space industry really taking off, there's a lot of billionaires, the Jeff Bezoses and Elon Musks and those Virgin Galactic type of folks are investing a lot of money, both for tourism, exploration, Earth observing planet labs, all types of folks that are going into space. So more and more people are investing and trying to understand how to operate and mitigate issues due to space weather. But NASA is not the largest space agency in the federal government. There are other agencies in the DoD and intelligence community that have more space assets.
Yeah. And we thought that an interesting last question for you, because we've been talking for about an hour, would be, what do you think is the most exciting thing in your field that's happening or that's going to happen, and what are your hopes for the future of the field of space weather?
So for space weather, there's a couple of things that couple together that's very cool. As I mentioned, Bell's law, where things are getting smaller and smaller, and you know about Moore's law as the capability. We're getting to the point probably in that next decade where we're going to have not only the capability of making multi-point observations globally on the ground and in space. So we have these constellations or dense arrays of instrumentation. We're also going to have the capability to actually analyze that data with physics-based models, many of them developed here at University of Michigan. There's a space weather modeling framework, which is actually used by NOAA's Space Weather Prediction Center as the community model to make forecasts. But all of these things are coming together. And so over the next decade, I can see a lot of advances. And one of the cool things about a computer simulation is you can test how many observations do I need to be able to characterize this? And then that will inform NASA or whoever to put, or NSF, the new instruments, or what parameter am I missing? My prediction is not very good, but now it's a computer, so I can start throwing things in and figuring out we need to make these. And so that interplay between the computer modeling, the computing, capabilities and constellations of missions are coming together. The other really exciting aspect of space weather is thinking about space weather impacting humans in other space environments. So we're going to have humans on the moon. And so we don't want dead humans on the moon. And if we have a permanent colony there, they don't have an atmosphere and don't have a magnetosphere. So we really need to have our predictions right, instead of saying, go out and collect a rock and say, oh, sorry, we didn't see that storm coming. Or on Mars. And if we discover life, so in February, we'll have a new Mars rover whose goal is to look for life. And probably in the next 15 years or so, we'll have landers on some of the icy moons. It could be a whole new, there's exobiology. We have to figure out how to remotely sense and figure out how these guys live or communicate or whatever they do.
Well, that's all sounds very exciting, and hopefully it progresses well and efficiently. So thank you very much for talking to us. We really appreciate it.
Yeah. Thank you so much, Professor Mulder. It was a pleasure.
It was fun. Happy New Year.
Thank you.
Hey everyone, thank you for listening to this podcast episode. This is Michael.
This is Sam.
This is Tommy.
And this is Joe.
If you're listening to this on YouTube, make sure to like, subscribe, and share with your friends. And if you're listening on Apple Podcasts or Spotify, make sure to leave a review. All of the show notes can be found either in the description below or on our website. Thank you again for listening, and we'll see you next week with more Everything Astronomy.